Let's talk a little bit about corrosion. So, corrosion is actually a big issue in our world, multi-billion-dollar industry trying to prevent corrosion. We can't. It's nature's way of dealing with things. We talked about energy and disorder as major themes in general chemistry, and they are the major themes of corrosion as well. They are creating disorder. So, we need to understand though that corrosion of metals is a redox reaction, and talk a little bit about corrosion prevention through cathodic protection and what we mean by a sacrificial electrode or sacrificial anode. So corrosion again is the result of the oxidation of the metal. So most of us know corrosion as iron, the red rust that forms, right? We think of rust. That's actually iron oxide. It's that red color. It's flaky, it falls apart real easily. I'll show you a picture in a sec. But that's what most of us think about when we think about corrosion. But that's just because iron has been corroded. Iron has been oxidized, it has lost its electrons, and what's left is its oxidation product. It's iron oxide. Most metals, like aluminum, will actually develop a thin oxide layer. Again, oxide is that corrosion product. And this coating will then prevent further exposure of the metal to oxidation. Iron, however, doesn't really behave very well. We see here, red rust. So again, corrosion, product of the oxidation of metal. Iron, the electrons, I apologize. Iron, especially when it's exposed to water, actually forms an electrochemical cell. So what's happening is electrons will travel through the water. The water acts as our media to help transport electrons. It also completes our cell. Meaning allows the anode and the cathode to touch. Electrons travel through the water from the anode to reduce oxygen at the cathode. The water is acting as your salt bridge, so it's completing the circuit, but it's also acting as a reactant. And so the iron 2 plus ions will also migrate towards the cathodic regions, and then rust accumulates. It's not exactly a great thing, right? And then we get this real brittle material, red rust. Each metal has an oxide product. Iron just happens to be red. Zinc oxide is a white product. Other metals have different colors they'll form. Some you don't even realize they're forming it. Some just will look more dull or gray in color, etc. And again, I say here that some metals often develop with an oxide layer that prevents further exposure of metal to oxidation. That is true. Like aluminum's really good about it. Aluminum forms a really quick oxide layer. If you go to your kitchen, if you have aluminum foil in your kitchen, that aluminum foil you have right there has an oxide layer on it. It's very thin. You can't see it really. You can't really see it, but it's there and it's protecting the aluminum from further oxidation. So a little bit kind of goes a long way. Copper does this as well. Copper forms a copper oxide layer that's actually used to help prevent corrosion from things like microbes. Microbial corrosion. The copper oxide layer is pretty weak on the copper, like it doesn't adhere really strongly to the copper metal, so the microbes build up, and eventually that oxide layer gets too heavy for the metal, and the oxide layer will just fall off the metal, leaving a new exposed copper metal underneath, but all those microbes are gone. Or you just walk by with a rag and you wipe off the top of that countertop and it wipes away those microbes as well. So metals are always doing this, just some metals have it worse than others when they form those oxide products. We can see here, your rust accumulation, your cathodic region, your anodic region, the overall reactions that are happening. We see the rust accumulating here. We see iron solid forming iron 2 plus. Over here, we see the oxygen reacting, the completion of the circuit as we go through. Why do we care and how can we prevent it? We care because it's expensive. Oxide formation and rust costs us money. It destroys products. We saw, if you look here, like at the building, that's not exactly advantageous. That's going to fall apart. And that costs us money to fix. So a lot of money is put in to prevent corrosion so we don't have to deal with it. We don't want to deal with the corrosion products. We want the material to stay good as it was originally intended for. And one way to do this is by using protective coatings. Protective coatings can include things like paints or metals that are deposited onto another metal to protect it. That's the use of a sacrificial electrode. So paint, what do I mean by that? I mean literally paint the material. Put a paint on top, put some kind of sealant on top. Will it protect the metal forever? No, it will not protect the metal forever. Nothing will protect the metal forever. But it will protect it for a period of time, hopefully prolonging the lifetime of that material to make it economically feasible to use it. So we just paint it. Why won't it last forever? Well, because the paint is going to break down too. And eventually either the paint will get scratched or nicked or worn away over time, and corrosion products will still begin, or the corrosion products will get onto the paint, burrow through the paint, and eventually reach the metal underneath. But it will prevent onset of it for a period of time, making the material more economically favorable to use. The other way to do it, again, is deposition of a more reactive metal. We call this electroplating. We talked about that in a previous module. Or electrodeposition. We're depositing a metal, we're plating a metal on one metal onto another. We do this by using a sacrificial metal. What do I mean by that? I mean a metal that's more willing to oxidize to protect something underneath. So here we see we've got an iron pipe, we've got a sacrificial electrode right here. A very common sacrificial material is zinc. Zinc readily forms an oxide layer and lets itself corrode away to protect the iron underneath. Why? Because of a difference in reduction potentials. Zinc would much rather oxidize than iron would. Zinc is fine giving up that electron, those 2 electrons in the case of zinc, to protect the iron underneath, until the zinc is of course destroyed. And so we call it a sacrificial electrode because it sacrifices itself to protect the iron underneath. And here's some examples of the way we can actually do this. This is like, this picture here is actually, let me make this bigger so you can see it. This picture here is actually a deposit of copper onto a stainless steel surface. Stainless steel is comprised primarily of iron, a little bit of molybdenum, a little bit of chromium. In here we see some more pictures. There's some molybdenum and nickel particles in here. There's, it's hard to see in here, but you can see some actual hexagons in here, some hexagonal shapes. There's actually zinc in here and nickel. And so there's zinc and nickel in these 3 samples. But they're different combinations of coatings that we can put onto stainless steel. In this case, put them all on stainless steel. We can put them on all kinds of materials. In this case, specifically, we use stainless steel. We plated these metals onto a stainless steel substrate or surface to protect it for a longer period of time. And what's pictured, the last picture here, this picture, is how we actually do it. We set up our electrochemical cell and we plate it. So what I've got going on here, it's hard to see, but coming in from the bottom down here is actually my stainless steel electrode, what we call your substrate, what we're plating on. This coiled wire here is my counter electrode. So the stainless steel that we can't see very well is my working electrode or my cathode. The coil is my counter electrode or my anode. This is a reference electrode. Just so we know how much cell potential is going through, and we're just plating the material on there to protect that stainless steel electrode underneath. One way you see this a lot is by galvanizing nails. A galvanized nail, you can buy these at the store pretty easily, pretty cheaply. Galvanized itself just means that a piece of iron or stainless steel has been coated in zinc to protect that iron underneath. So galvanization is the process of plating zinc onto the material. We can also study these corrosion materials to see how long we think they'll last. And here's just some examples of how we can do it. This setup here is just an actual setup of when I was still in grad school, me doing corrosion studies. I had each one of these beakers have a different electrode in it that has been plated with a specific material, and they're just sitting in a salt solution, and I'm monitoring their corrosion product over time, seeing how long it takes for them to corrode. The graph here tells me a lot of information. It tells me when the oxide layer has been formed and when that oxide layer is breaking down. So the materials start out, the materials start out here, here, and here. Up here is where the oxide layer has been formed. So you can see how many days specifically it took for that oxide layer to form. For nickel, a nickel cerium oxide coating and a nickel cerium oxide ferrocene coating. We can see that our oxide layers form pretty quickly for the nickel cerium oxide and nickel cerium oxide and ferrocene and the nickel itself. Oxide layers form pretty quickly, but we also see that the nickel itself, plain nickel coating, its oxide layer is destroyed pretty quickly, and now the reason this moved down here is we're actually corroding the nickel material itself, which is what we're trying to protect. The one in green, the nickel cerium oxide, we see that its coating held on for a little bit longer, a few more days than the nickel did, but again, it drops because we started destroying the nickel coating itself. Now it's starting to grow again here, it's starting to increase again. That's because it's actually forming a new oxide layer underneath. But the nickel cerium oxide ferrocene, not perfect. No, nothing's perfect. Like I said, unfortunately, nothing's ever going to be perfect. But it formed its oxide layer, and it's holding pretty tightly compared to the other two materials. And we see that in the pictures as well. The top picture is when the coating was first formed with no exposure to corrosion. And the bottom picture is after it's been submerged in salt solution for 30 straight days. We see the nickel has not only destroyed the coating, but it's actually destroyed the nickel substrate underneath because the coating is on top. It's a nickel coating on top of the stainless steel. So the nickel coating has been destroyed, the stainless steel has been destroyed. For the nickel cerium oxide, we can see the coating versus the coating is starting to be destroyed. It hasn't quite reached the substrate yet, but it looks like we're going to get there. In the nickel ferrocene, we can see a little bit of corrosion throughout the coating, but again, comparatively, it's holding on to its own pretty well, and the coating is not.